Today we're going to talk about periodic trends. Now, we have a periodic table here, and it's divided up into columns, where elements in each of these columns share similar characteristics. And this is all due to them having similar electron configurations. Now, this first column here, right below hydrogen, all these have one valence electron, and because of that, they all have very similar chemical characteristics. Then, if we look at our second column, here below beryllium, they all have two valence electrons, and again, share very similar characteristics. Then we can skip the transition metals here, and we get to boron for our third column. Our fourth column has carbon and the species below that. Then our fifth column we have nitrogen. In our sixth column we have oxygen. In our seventh column we have fluorine and the other halogens beneath that. And then we get to the far right column here, our eighth column. And the special thing about this column is that they all have a noble gas configuration for their electrons, or all their electrons have filled energy levels. And we call this last column here the noble gases. And they're not very reactive. In order to react, they have to take on another electron. In order to take on another electron, they have to add a whole nother energy level. Now, this can happen, but it's less likely to as reference to energy. Now, as far as reactions go, or chemicals react with one another, or their reactivity, we can take any element. They tend to go towards a noble gas configuration where they have all their valence energy levels filled. And because of that, there are certain characteristics that happen. And when we have a particular charge that is associated with a certain column in the periodic table. So I'm going to go through and tell you what these typical charges are for each of these columns. So if we look at this, if we look at lithium, lithium can gain 1, 2, 3, 4, 5, 6, 7 electrons in order to get to a noble gas configuration. Or it can do a secret option and lose 1 electron to get up here to helium and again attain a noble gas configuration. So we have to ask ourselves, which is going to be easier for lithium, to gain 7 electrons or lose 1 electron? As you might have guessed, it's going to be easier for lithium to lose 1 electron, and that's going to give it a positive 1 charge. Because electrons are negative, losing 1 is going to give it a positive 1 charge. Then we can look at beryllium here, and it can either lose 2 electrons or gain 6 electrons. And it's going to be easier for it to lose 2 electrons and have a positive 2 charge. Similarly for boron, it's going to be easier for it to lose 3 electrons, giving a positive 3 charge. It is possible for it to gain 5 electrons, but it's a little bit more favorable energy-wise for it to lose those 3 electrons and have a positive 3 charge. Then we get to carbon. Now carbon is a little odd. It can gain 1, 2, 3, 4 electrons to get up to neon's electron configuration, or it can lose 1, 2, 3, 4 electrons to get to helium's electron configuration. Now both ways get to a noble gas configuration, and they're both honestly equally viable. So for carbon, it can kind of go either way. It can either have a positive 4 or a negative 4. It really depends on what it's reacting with. And this will become a little bit more obvious when we start referring to oxidation numbers. But just for now, except that it can kind of go either way. Then for nitrogen, generally it's easier for it to gain 3 electrons, so it's going to have a -3 charge. It can be a +5. It can lose 5 electrons and be +5. That's definitely possible. But energy-wise, it will tend to be a little bit more likely for it to gain 3 electrons and have it at -3 charge. Then for oxygen and the species below it, they will normally gain 2 electrons, giving a -2 charge. And for fluorine and the elements below that, or the halogens, they will normally gain 1 electron and have a -1 charge. And then lastly, for the noble gases, they don't normally gain or lose electrons, so their charge will be 0 generally. So one of the things with this is that we can kind of summarize this stuff with the octet rule. The octet rule states when atoms bond, they will lose, gain, or share electrons to attain a filled outer energy level of 8 electrons. Now the reason for this is if we look at our second row here, if we count 1, 2, 3, 4, 5, 6, 7, 8, 8 valence electrons, that'll get us up to the noble gas configuration. If we look at the third column, it's the same thing. If we go 1, 2, 3, 4, 5, 6, 7, 8, it takes 8 electrons to get up to a filled valence electron energy level. So this is where the 8 comes from in the octet rule. It takes 8 valence electrons in order to fill the outer energy level. And this is why it's referred to as the octet rule, where oct means 8. Now to investigate this just a little bit more, I do want us to take a look at neon. So if we look at neon, we can have the first energy level here, the 1s orbital, and if you don't know what 1s is, don't worry about it. If it's Greek, just don't worry about it. I'm just stating it for those who have heard about it. We can fill in our electrons, so 1 for hydrogen and 1 for helium. And I'm going to represent my electrons with just a simple line. So we'll have 2 electrons here. Then we can go down to the second row. So each time you look at a different row, this is essentially another energy level. So we're adding on another energy level since we dropped down a row. And we can look at 1, 2, 3, 4, 5, 6, 7, 8. So we'll have 8 electrons in this energy level. And so we'll go 1, 2, 3, 4, 5, 6, 7, 8. Alright, so now our neon has reached this electron configuration, has a filled outer energy level here, and so it's a noble gas, so it's not going to be very reactive. Now, if we were to say, alright, it does react and it's going to gain 1 electron, it's going to go up to the same electron configuration as sodium here. In order to do that, we have to add on a whole nother energy level. And then we can add on an electron. Now, the thing with trying to add on this electron is neon is only going to have our 10 protons associated with it. And so those are going to be what have to attract this electron to stay on. The problem is that we have all these other electrons here, these inner electrons or core electrons, shielding that nucleus from this new electron we're trying to add. And so this is why the octet rule holds true and why things tend to go towards trying to fill their energy levels and then really nothing else after that, because it's just not that favorable to add on a whole nother energy level for this 1 extra electron. Now, there are some exceptions to the octet rule. One of the big ones would be hydrogen. So if we look at hydrogen, it only needs to gain 1 more electron to get to a filled octet or a filled outer energy level and have a noble gas configuration of helium. So it can either gain one here, or it could lose one and not have any electrons around it and just be a free-floating proton. Both of those are equally viable. So for hydrogen, it can either gain one electron or lose one electron. And in that sense, hydrogen here is actually very similar to carbon in that it actually depends on what it's reacting with. And this will have further implications later on when we start talking about oxidation rules and electronegativity. But electronegativity wise, the ability to gain electrons, hydrogen and carbon are actually very similar. So, hope you learned something about periodic trends, and I look forward to talking to you again next time.